Hello students, welcome to the digital learning of session 2 of unit groups of BSc 3rd Sem Mathematics. I am Dr. Shashikala. In this session 2, let us discuss about examples on abelian group. Firstly, show that square root of unity is abelian group with respect to the x. So let us take the set g is equal to 1 comma minus 1 under the operation multiplication. Let us frame the table here. 1 and minus 1 in the row and in the column also element 1 and minus 1. So 1 into 1, the operation here is multiplication. So 1 into 1, 1. 1 into minus 1, it becomes minus 1. Again in the third row, minus 1 into 1, minus 1. Minus 1 into minus 1 becomes the 1. So to prove it for abelian group, we have to verify for the following laws. Firstly, we have to verify for a closure law. All the entries of the elements in the table are in the set G, hence closure law is valid, is verified. So whatever the elements we got it after the operation of the multiplication is within the elements of the group. So that is 1 and minus 1, minus 1 and 1 what we got is there in the elements or there in the set G. Therefore, closure law is verified. Nextly, verify for a associative law. To prove it for a associative law, we have to consider the three elements from the group. So now we are considering 1, 1, minus 1. We can also consider 1, minus 1 and minus 1. So to prove it for associative law, three elements be required and LHS side and RHS side has to be equal. In the LHS side, bracket is taken for 1 and 1. Outside the bracket, minus 1. In the RHS side, 1 and minus 1 is taken inside the bracket and outside the bracket we are going to consider 1. So with the operation, with the multiplication, we got it as minus 1 and minus 1 on both the sides. Therefore, associative law is verified. So nextly, we will verify for a identity law. So how we are proving for identity law means again taking the help of the chart. So the topmost row, if you are considering, it is a 1 and minus 1. The same element is repeated in the second row. So therefore, the element which is repeated as in the first row, the column has to be considered. In the column we have the element as a 1, that becomes the identity element. So identity element is 1 here. So therefore the row heading 1 is same as that of the topmost row. Therefore identity law is verified. Nextly, to verify for an inverse law, see, inverse law means again taking the help of the identity law. Identity law is giving the identity element as a 1 here. Therefore, in the second row, if you are observing, where we got it as a identity element 1, so with the multiplication of 1 and 1. In the third row, 1 we got it with the multiplication of minus 1 and minus 1. So therefore, inverse of 1 becomes the 1, inverse of minus 1 also becomes the minus 1. So now every element has its inverse, therefore inverse law is verified. Lastly, to verify for a commutative law, the table is symmetric with respect to the principal diagonals. So if you are observing the chart, so diagonal elements we have to consider. The diagonal element is having a symmetric elements 1 and 1. So therefore we can say that it is a commutative law is verified. Therefore all the laws is verified here. The closure law, associative law, identity law, inverse law and the commutative law. Therefore we can say that abelian group, G is an abelian group under the multiplication. Next problem is cube root of unity is abelian group under the multiplication. To prove it for that, let us take the element 1 omega omega square under the operation multiplication. As we have done in the first problem, so we have to frame the chart, we have to frame the table here. 1 omega omega square in the row, 1 omega omega square again in the column. So 1 into 1, 1. 1 into omega, omega. 1 into omega square becomes again a omega square. So in the third row, omega into 1 becomes omega. Omega into omega becomes omega square. Then again, omega into omega square becomes the omega cube. But omega cube is not present in the set G. So with the difference of omega square is there, but we got it as omega cube. So therefore we are going to write it as a 1 here. Then omega square into 1, omega square. Omega square into omega again becomes the 1. So omega cube value is, remember, it is a 1. Omega square with the omega square, it becomes the omega. So let us go for a proving of the laws. The first law is closure law. All the entries in the table are elements of the set G. Therefore, closure law is verified. So, elements means after the operation we got it 1 omega omega square. So, we have not got after the element of omega square here. Within the omega square only we got it the element. Therefore, all the entries, all the elements which is there in the table is from the group G only. Therefore, closure law is verified. Nextly, associative law. To prove it for associative law, 3 elements has to be considered. Let us take the 3 elements 1 omega omega square. So operation, remember, is it is a multiplication. So bracket we are taking for a 1 and omega in the LHS side. Omega and omega square is taken, the bracket is taken for omega and omega square in the RHS side. So after the multiplication, we got it as omega cube on both the sides. Omega cube answer is 1. So therefore, associative law is verified. Nextly, to verify for identity law, as we have verified in the previous case, the topmost row is having the element as 1 omega omega square. In the second row is same element repeated. Therefore, the identity element here is 1. So therefore, the row heading 1 is same as the topmost row, therefore identity law holds. Similarly, the inverse law. So, taking the help of the identity law as 1, identity element as 1. So, 1 we got it with the multiplication of 1 and 1. Next, in the third row, 1 we got it with the multiplication of omega and omega square. So, in the fourth row, 1 we got it with the multiplication of omega square and omega. So therefore, for the inverse of 1, the element is 1. For the inverse of omega, we got it as omega square. With the inverse of omega square, my answer will be omega. So now that we have shown it here. Every element has an inverse, therefore inverse exists. The commutative law. To prove it for a commutative law, again table has to be considered with the principal diagonal here. So principal diagonal, we got it as a 1. Therefore it is symmetric. So therefore we can say that it is a commutative law, holds good. So all the laws is verified here. Therefore we can say that G is abelian group under the multiplication. Next problem is, prove that H is equal to 1, 2, 4 is a subgroup of group G where G is equal to 1, 2, 3, 4, 5, 6 under the multiplication mod 7. So the group G is 1, 2, 3, 4, 5, 6 element is present. So operation is multiplication modulo 7. So subgroup is 1, 2, 4. Again the chart is table is framed here. In the row 1, 2, 4, in the column 1, 2, 4 again. So in this problem I have clearly explained how the elements we are going to get it within the table. 1 into 1, 1. 1 into 2, 2. 1 into 4, 4. Again in the third row 2 into 1, 2. 2 into 2, 4. 2 into 4 is 8. But we can't write it as a 8 because it is not within the multiplication modulo 7. So therefore with the difference of 1, we got it as a 1 in the table. So again in the last column 4 into 1, 4. 4 into 2 again 8. Therefore we are writing as a 1. 4 into 4 is 16, but we can't write it as a 16 here. So therefore So here I have clearly shown with the division 4 into 4 becomes 16 but does not comes under the 7. So if you are dividing, remainder becomes the 2. That remainder we are going to write it so within the table. Next, closure law has to be verified. All the entries are there in the table is same as the elements which is there in the edge. Therefore, closure law is verified. So, associative law, elements of the subgroup we have to consider 2, 4, 2, 4 and 1. So, bracket in the LHS side is for 1 and 2. Outside the bracket, 4 has to be considered. Then in the RHS side, bracket is for 2 and 4. Outside the bracket, we are going to consider as a 1. With the operation, see in the LHS side 2 and 4, 2 into 4 becomes the 8 with the difference of the 1 with the multiplication modulo 7. So in the RHS side, again 1 multiplication modulo 7 of the 1. So therefore if you multiply 1 into 1, it becomes the 1. So on both the sides we got it as a 1. Therefore H is associative here. Nextly, identity law. So if you are observing the topmost row is 1 to 4, the same element is repeated in the second row also. If you are observing the arrow mark, the one I marked it, so with the arrow mark, so this becomes the identity element. So row heading 1 is same as the topmost row, therefore E equal to 1 is the identity element. Nextly, to go for an inverse law, if you are observing again the table, so with the help of the identity element as a 1 we got it with a multiplication of 1 and 1. Then in the third row, 1 we got it with a multiplication of 2 and 4. In the fourth row, 1 we got it with a multiplication of 4 and 2. So inverse of 1 becomes 1, then inverse of 2 becomes 4, then again inverse of 4 becomes the 2. So every element has a inverse here. Therefore we can say that H comma multiplication modulo 7 is a group. Therefore H is a subset of G. Therefore H comma multiplication modulo 7 is a group of G comma multiplication under the operation multiplication. So let us take one more example of the abelian group. So of fourth root of unity here with respect to the multiplication. So let's consider a set G 1, minus 1, I and minus I of the multiplication under the operation multiplication where I is equal to square root of minus 1. Let us frame the table here. So in the row, let us take 1, minus 1, I and minus I. In the column also 1, minus 1, I and minus I. So let's take the multiplication of for the first row 1 and 1, 1, 1 and minus 1, minus 1, 1 and I. 1 and minus I becomes the minus I. So again in the third row the multiplication is minus with the minus 1 and 1, minus 1, minus 1 into minus 1 becomes 1, minus 1 into I becomes minus I, minus 1 into minus I becomes the I. Similarly for a fourth row and the fifth row we can take the operations. Let us verify for first law, the closure law. All the entries in the table are the elements of the set G. So whatever we have got after the operation of the multiplication, so that is the values are, we got it as 1, minus 1, I and minus I. These are the only elements we got it. So these elements are there in the group G. So therefore we can say all the entries in the table are elements of the set G. Hence we can say that it is a closure law under the group G. Nextly, to verify for associative law, let's take the three elements from again group G only. The elements are 1, minus 1 and I. So let's take the operation for the associative law. Operation is again a multiplication. So in LHS side, bracket is for 1 and minus 1. In the RHS side, bracket is for minus 1 and the minus I. Outside the bracket in the LHS side, we have an element I. Outside the bracket, the elements which is there in the RHS side is 1. So after the multiplication, we got it on both the side as minus I. So we can say that associative law is verified. The identity law. To verify for identity law, as we have already seen, in the first row we have the element as 1, minus 1, I and minus I. The same element is repeated in the second row also. Therefore, identity element is 1 here. So next, to verify for a inverse law. So again, taking a help of the identity law is 1 here. Identity element from the identity law is 1. So in the chart, if you are observing, so 1 we have got in the second row with the multiplication of 1 and 1. In the third row, 1 we got it with the multiplication of minus 1 and the minus 1. In the fourth row, we got it as 1 with the multiplication of I and minus I. So in the last row, 1 we got it with the multiplication of minus I with the I. Therefore, the inverse of 1 becomes the 1. The inverse of minus 1 becomes the minus 1 again. Then from the fourth row, the inverse of I becomes the minus I. Then in the last row, the inverse of minus I becomes the I here. So therefore, every element has its inverse. So inverse exists. Last law is commutative law. So again, we are concentrating on the symmetric operation, symmetric diagonal elements here. Symmetric diagonal elements is a symmetric here. Diagonal, principal diagonal elements are symmetric here. Therefore, we can say that commutative law holds good. Therefore, G is abelian group under the multiplication. That means all laws are verified here. So associative law, closure law, identity law, the inverse law, commutative law, all the laws are verified here. Therefore, we can say that it is a abelian group under the multiplication.